Afternoon. Welcome to this first lecture post mid-sem. Um, so as I said, there's going to be a little brisk now with our coverage on some amount of convergence. And you already got a flavor of that during midsems. I know midsems were a little lengthy. We'll have a discussion around it on Saturday at 11 a.m. Friday is a holiday, right? So Saturday we'll have 11 a.m. discussion around the midsem solutions. I'll post the solutions. So having done the convergence part a bit, um, um, we'll just quickly recap what we discussed about convergence rate for smooth functions just before midsems. So given an L smooth convex function, gradient descent with step size gamma equals 1 by L achieved a solution in R square L by epsilon iterations. And this step size was basically to give a lowest upper bound. Right? In practice, you would have some iterative techniques like line search or ray search. I'll put some optional slides on that, how line search, ray search gets done with certain conditions called the Armio conditions, strong wolf conditions. And in fact, I'll that those conditions will become more relevant when you look at convergence proofs or convergence analysis, especially with some of the accelerated generalized gradient descent algorithms. So now we look at smooth and strong convex. So with smooth and strong convexity, can we do better? Is a question. It is only with smoothness, but with strong convexity. Can we do better with strong convexity without necessarily smoothness? Right. So what is interesting in this picture is the gap between smooth and strong convex functions, right? So this picture is interesting to keep in mind. So again, recall that with a strongly convex function, you have a quadratic upper bound or lower bound? Lower bound. The quadratic lower bound, right? So Lipschitz continuity, etc., are with quadratic upper bound. So we have this gap. The closer the lower and upper bound curves are, the better conditioning of behavior the algorithm we would expect to be, right? So in some sense, the combination of smoothness and strong convexity is also giving us the opportunity to look deeper into the space. Okay. So here you go. Upper bound and lower bound. So the other interesting part is if you're looking at the Hessian and the eigenvalues of the Hessian, or look at the strong convexity factor mu, you could relate them to the eigenvalues. Okay, the eigenvalues associated with the Hessian matrix. So here you see the lambda max by lambda min. And we can show that the lambda max by lambda min of the Hessian is upper bounded by L by U, right? L is associated with the upper bound Lipschitz smoothness. Mu is associated with the lower bound strong convexity. Okay, so this lambda max by lambda min are typically upper bounded by L by mu. Well, L is here. and mu is here. Okay. These lambda max and lambda min are for the Hessian. Okay, the function itself is somewhere here. I'm sorry, I should have made them touching here. So my bad. So let's say this is the point we're considering. The point x. To say Hessian of f at x. Okay. So do we get a convergence rate which is somewhat related to the L by mu, actually mu by L, the min by max, right? So in linear algebra, trying to solve a linear system, you also have come across this conditioning number, right? The ratio of the smallest to the largest eigenvalue. Matrix is supposed to be conditioned when the small to the largest is very large, right? Or very small. That's small to the largest, very small. Ill conditioned. They're very skewed. The smallest and largest eigenvalues. So in some sense, we're saying that if the gap is very wide between these two, the behavior of the function is going to be a little wobbly. So can we bring some regulation to the behavior of the function? So let's consider this fastest convergence. This is like one of the fastest convergence we can get, okay? And since you guys have now familiarity through your midsems, right? With the entire convergence rate, I'm not going to write too much on the board. You have a question? Okay, so recall from analysis 1. You have all have your notes, right? Open your notes. You remember this analysis 1, where we had put a, express this inequality of equality, the dot product between the gradient and difference of the iterates from the optimal x star. Okay, we just used simple algebra. This total algebra, nothing more. Straightforward algebra. Okay, so recall that this is the trick 1 derivation. Instead of convexity followed by telescopic summing. Now the question is, why not use strong convexity next? So what we did earlier was convexity followed by some telescopic summing. To recall your initial analysis, we're saying, well, let's apply strong convexity directly. Why strong convexity? Why are we tempted to use strong convexity so early? Anyone? Sorry? Correct. Strong convexity will provide a lower bound on the left hand side. Okay. The strong convexity provides a lower bound on this GT transpose xt minus x star. Sorry, I should have written this in green. This GT transpose xt minus x star this is upper bounded by a term that involves the strong convexity. What is that strong convexity? ft minus fx star plus mu by 2 xt minus x star. That's what the pink curve is, right? This is a quadratic curve. Okay, so now we just put 1 and 2 together. Say, well, we'll basically apply the lower bound to the right hand side of 1. That's what we did. And we did a little bit of rearranging. So basically we took the gamma by 2 norm GT square on the other side. With all of this, with no more casualty or with no more chain terms cancelling out, we have xt plus 1 minus x star square. And xt plus 1 has basically come because of this term here. This term here is less than equal to 2 gamma f of xt minus f of x star minus f of xt plus gamma square gt square. So the part in grays has just come from the strong convexity. The part in yellow has come from your linear algebra earlier. Okay, it's pretty much color coded, so you can just plug and play. Now the part I have put in green here is one you should observe. So this is probably the important term here, which will probably start getting us close to this mu by L or L by mu. Okay. So how have we got this? We've got this because there's a mu by 2 xt by x star square here. And there is an xt by x star square that came from the yellow, right? There was xt minus x star that came from the algebraic term and xt minus x star that came from the strong convexity inequality. That is important. We just put them together into this slightly differently colored grid 1 minus mu gamma xt minus x star. That's the only change that has happened. So this term has now caught our attention. Okay, so what can you do now next? So instead of making it monotonous, I'm going to ask you, well, what will you do next? This one, 2 gamma. What will you do that on that? Can I do any telescopic summing anywhere? Sum across all values? Minimize with respect to? Minimize with respect to gamma, okay. But any other ideas? So one is telescopic summing, one is minimize with respect to gamma. But why not go for telescopic summing first? What's the problem? If I do xt plus 1 minus x star square summation, what would happen? I mean, see, there's a 1 minus mu here. So we'll have a multiplication. Do you understand? Unlike earlier telescopic summings, something 1 minus mu gamma will keep getting multiplied. Okay, and that probably explains why we'll get a log in our convergence. Remember, that was our very sought after convergence rate, right? Something log, you remember, log of 1 by epsilon. Maybe time is right for log of 1 by epsilon. So let's try doing that. Okay. So I again just recover this important equation. So now if I do telescopic summing in mind, what will happen? Across all xt plus 1 square. No, across all t, sorry. And what will be the lower bound? Lower bound index for t? T will be from 0, right? T will be from 0 until capital T minus 1. Okay, let's try writing this down. So telescopic summing I'm doing after dividing both sides by this 1 minus mu gamma t plus raised to t plus 1, because I anticipate that 1 minus mu gamma will keep getting multiplied. Okay, so in the interest of time, I'm not going to write all this on board. here you have, so 1 minus t gamma, mu gamma raised to t plus 1 divided on the left hand side, divided here as well. And you'll have xt minus x star 1 minus mu gamma raised to t. And you'll have a similar in summation on the right hand side. Okay. The only difference is here we have t plus 1, the denominator, here you have t, the denominator. Exponent is the slight difference. So what happens if you sum? Is there any cancellation? Yes. Any cancellations? What cancellations? That, yeah, so the t plus 1 here obviously is going to cancel against the t here, no? Somewhere. Because this indices here, xt and t, both are same. I think that's the intuition you should, that should strike you, right? Here's a t and here's a t plus 1. But the t plus 1 is also the index here and the t is the index here. So there will be consecutive terms that will get cancelled out in the summation. Okay, so with all of that, you will get, finally, you only have xt minus x star norm square 1 minus mu gamma raised to capital T. And the initial t equals 0 will just give you 1 in the denominator. Okay, for those who are not getting it, you have to sit down and write. This is important step to register. I anyways released the video of last year. So, okay, this part, this is very religiously being done. So I'm just summing across all values of t. There seems to be no relief here. Do you think there'll be some relief here possible in the blue term? Something can get cancelled out. GET norm square. So you're saying we have not yet used smoothness. Can we bring in smoothness here? Is that a point? Good. I'm really happy. Some of you are suggesting you write things down. Some of these, steps will actually, prompt themselves, right? So writing is very key here. So the moment I wrote this down, there is a possibility that emerges. With smoothness, something I can do about GT norm square. Let's proceed. Okay. So I've just written this telescopic summing. I'm going to get to the telescopic summing here. So I've done one more thing. Sorry. Before telescopic summing, I've actually written the Lipschitz smoothness as well. So you can what you are anticipating that you'll do using Lipschitz smoothness, I've written it down right away. So you can do telescopic summing before Lipschitz smoothness application or after also. So here, right, based on my rough work on the previous slide, I've kind of suggested, let me do Lipschitz smoothness, let me bring it up front and then do telescopic summing so that I don't have that. So I don't have the scary term here. This is a very scary term here. Can we avoid the scary term? Okay, so I've done this here. Okay, f of xt plus 1 is less than equal to f of xt minus gamma gt square gt norm square plus L by 2 gamma square g norm gt square. You remember this? This part is from Lipschitz smoothness. Okay, so then I have this. Now will it help us simplify this scary expression from the previous slide? Also recall that we had gotten rid of this gamma by minimizing it, the RHS with respect to gamma, right? That got us as f of xt minus 1 by 2 L norm gt square. Perhaps some of those tricks might also resurface. The other important thing is f of x star is less than equal to f of xt. Okay, so maybe that can also be helpful in simplifying some of these expressions. So then we are tempted. Can we substitute gamma equals 1 by L somewhere? So see, a lot of this rough work you can do yourself, right? Write down possible simplifications. Okay. Let's again go by step. So indeed, it turns out that I can do some minimization. If you recall, I could minimize the right hand side for gamma equals 1 by L. Right. So that telescopic summing, now I'm trying to simplify my job there. So for gamma equals 1 by L, this right hand side is minimized, and now I get a simpler expression. F of x star is less than equal to f of xt plus 1, which is less than equal to f of xt minus 1 by 2L norm gt square. Okay, am I now ready for some telescopic summing? So the telescopic summing term I had, right? I'm trying to get some bargaining done for it beforehand. So what I'll do is this f of x star minus f of xt plus gamma square gt norm square, right? This term, I'll try and show that it's less than equal to 0. Okay, so this was the same term that came up in the telescopic summing. Okay, I again remind you here 2 gamma f of x star minus f of xt plus gamma square gt square. This scary term, now I'm trying to prepare and show that that is less than equal to 0. So if I substitute gamma equals 1 by L, right, basically I'll get this interesting expression, 2 gamma f of x star minus f of xt plus gamma square gt square. I just substitute for gamma here, and I'll get minus 1 by L square gt square plus 1 by L square norm gt square. Okay, because of this inequality. I've also color coded to make things easier to understand. Okay, so see this part, f of x star minus f of xt is less than equal to 1 by 2L or minus 1 by 2L norm gt square. So I've just substituted this blue part here, right? This part has been substituted here as inequality, as an upper bound for this part in gray. Okay, with all of this, these two get cancelled out, these two terms. So therefore, I have my formidable term in the telescopic sum to be shown to be less than equal to 0. Okay, so just note these. For gamma equals 1 by L, I use this inequality, plug this 1 by 2L norm gt square, negative of that, to be this component, and now I have the right hand side to be less than equal to 0. Okay, so now again recall from the previous slide, we had this term, and this term I've shown to be less than equal to 0. The yellow plus gray has been shown to be less than equal to 0. Okay, so we have just packed everything together. I've said, well, this part is less than equal to 1 by mu by 1 minus mu by L xt minus x star norm square. Right? Now, what is this? So gamma is 1 by L, right? Now I can use gamma is 1 by L. Now, what do you know about L by mu? L is supposed to be greater than equal to mu, right? L is like lambda max, mu is like lambda min, or upper bound for lambda max, lower bound for lambda min is R, L, and mu respectively. What do you expect this to be? L by mu? Greater than equal to 1. Right? Therefore, 1 minus mu by L will be Sorry, will be greater than or equal to? Yes. One minus mu by L will be greater than or equal to 0. But is that all? Will it be less than or equal to 1 also? I can also show that. I know that mu by L. Okay. Anyways, I know that. And I know that mu by L. Mu by L is also less than or equal to 1. So by basically multiplying by something which is less than between 0 and 1, this term is bringing a dampening effect to the term on the left hand side. It's becoming multiplicatively smaller. This is an epsilon between 0 and 1, right? And all this comes because the Hessian is or Hessian minus, or rather Li minus Hessian is positive semi-definite, and Hessian minus mu I is also positive semi-definite. Hessian minus mu I is positive semi-definite because of strong convexity. Li minus Hessian is positive semi-definite because of Lipschitz smoothness. Okay. So we have packed everything. Now it turns out that this notion of Q linear convergence. So again, we won't have time to talk about all of those. I'll put those extra slides. But the idea of Q linear convergence is as follows. I've just summarized it here. V1 to Vk is Q linearly convergent. If V raised to the Vk plus 1 minus V star divided by Vk minus V star is less than or equal to R for some R between 0 and 1. Okay, so this looks exactly like that, right? Xt plus 1 minus x star divided by xt minus x star norm square is less than or equal to 1 minus mu by L. By mu by L is R here. Okay, so yeah, and you can show that eventually x capital T minus x star norm square divided by 1 minus mu by L raised to T is less than or equal to x naught minus x star norm square. Keep applying this. So that is what we are coming to, right? So multiplying all the terms. This is effectively what we are doing, is applying that telescopic summing. Many terms are getting cancelled. So now you can see why that log of 1 minus epsilon is where it is coming from, right? However, the problem is as follows. We wanted order 1 by epsilon, but it has to be in terms of f, not x. Okay. So what we seek is convergence of the function and not the x. What do I do? Lipschitz continuity. Okay. What else can be done? We haven't used one property. At x star, what do you expect the gradient to be? 0. See, x star is not some random point, right? So could I use convexity again? Should I use Lipschitz? So I can probably pull back any of those properties, obviously judiciously, such that there is a gradient at x star. So at x star, I need the gradient to vanish. Okay, so this is why x star gradient should vanish. Let's try and get there. So what we do is we'll use smoothness and the fact that gradient of f at x star is 0. So what have we done? We use the same smoothness property, xt minus x star less than or equal to so for xt minus x star, I'll come here. And the gradient is evaluated at x star, which will go to 0. So f of xt minus f of x star is less than or equal to L by 2 xt minus x star. By choose smoothness. right? So smoothness gives you an upper bound of xt minus x star. Strong convexity gives you a lower bound. So that's what we're using. We are using upper bound here. So just keep this in mind, right? Lipschitz smoothness gives you upper bound, convexity, strong convexity, lower bound. Based on where you're stuck, just pick up one of them. So that's what we did. Lipschitz smoothness because we wanted an upper bound here. So we did this, applied this L by 2, xt minus x star. Now I'm set, right? So f of xt minus x star, I can just put it in here. F of xt minus x star is less than equal to L by 2 xt minus x star, which is less than equal to L by 2, 1 minus mu by L raised to t x naught minus x star. Now x naught minus x star is okay. X naught is a point I chose, right? How did I choose x naught minus x star in the part before midsem? What did I assume? Sorry? Starting point to optimal, and that it is not too far. Right? If it's too far, you're bad luck. I mean, you should be within some radius r. The further away you are, the more time you will take. So we can put that x naught minus x star is less than equal to some r. Right? Okay, this is important. Okay, so this trick we have not. I mean, you see somewhere we are stuck badly. Tricks like this are very helpful. Okay. So setting r square is x naught minus x star square. We have now got this. Now what do? F of xt minus f of x star is less than equal to L by 2, 1 minus mu by L whole raised to t r square. If I want to get within epsilon radius of f of x star, how many iterations will I require? I'll require L by the right hand side to be less than equal to epsilon. Right? And that will lead to t to be. So just this is interesting. Right? This is just interesting, this entire expression. We are saying that at the teeth step, you are within x star subject to or in terms of your within x star in terms of how nicely you are packed between the Lipschitz smoothness quadratic and the strong convexity quadratic. Right? Really surfacing here. Of course, into r square. So to get an error of epsilon, we will have to ensure that this right hand side is less than equal to epsilon, which will imply that t should be at least order of this log of 1 by epsilon. Okay. Okay, so here's the kind of summary, right? Earlier we had t greater than equal to 1 upon epsilon. We start with very bad epsilon square. Sorry, we start with epsilon, right? Then epsilon. Yeah, epsilon square and then epsilon. Now log of 1 upon epsilon. Now let's see how this fares, right? To get an error of 0.01, we only need L by mu log of 50 r square L iterations. In the smooth case, which was without strong convexity, we required 50 r square L. There was no log term here. So it was really helping. Strong convexity really helped. So here's the summary. Lipschitz continuous function 1 by epsilon square. Lipschitz, smooth functions, we got 1 upon epsilon. Smooth plus strong convexity, we got log of 1 by epsilon. And you can see concretely what happens, right? Yeah, you can see you go from epsilon 0.1 to 0.01. In the case of C, which is Lipschitz continuous, factor is 100 times more. In the case of strong, smooth functions, this factor is 10. But in the case of strong convexity, there's no multiplicative factor, it's just additive factor. Okay. So it is from 8.49 iterations to 13.49, just 5 more iterations. You see the power? And this actually manifests, right? So regularizer does make a big difference in convergence. People have run experiments and found that adding a regularizer suddenly get much faster convergence, even for non-convex functions. So the optimization is going to be an important field forever, right? I mean, as long as machine learning needs to happen with large number of parameters and under compute constraints. So it's a very interesting thing that you got constant step size increase for 10-fold higher precision. So this is the idea of Q linear convergence. I'll post optional slides on Moodle. You can look at it, but the basic idea is already conveyed here. It's called linear because it's linear in the number of steps is now linear, even with the multiplicative epsilon. Okay, now what? Are we all set? What would be the next question I would ask? So all this is fine. Is there a combination I have not explored here? And in fact, a combination that I have not explored here can also help me push the frontier of algorithms themselves. So let me write these questions, right? How about strong convexity plus Lipschitz continuity, right? So we already saw that just Lipschitz continuity gave you, let's write this expression down, R square B square by epsilon square. Okay. Smoothness gave you R square L by epsilon. Smoothness plus strong convexity SS gave you L by mu log of R square L by epsilon to epsilon. Do you think strong convexity and Lipschitz continuity will so none of these had strong convexity and Lipschitz continuity, right? Where do you think it will fit? What's your guess? Min between SS and S. Okay, so your guess is it will fit somewhere here. What that form will be, we don't know. Could be square root of epsilon, you think? Right? So that's one question we'll ask. But let's ask another question also before I proceed. Okay. So these are all saying, well, T will take at least so much time, right? All of these are inequalities where T is greater than or equal to. In this cases, we said T greater than or equal to for all these cases. So question, is there some upper bound? And if somebody told you, oh, for Lipschitz continuity plus strong convexity, you can get 1 by epsilon. Let's say you work hard and show it's one square root. I'm not saying it's square root. But somebody says, oh, no, it will not take more than 1 by epsilon or whatever, right? Then what will you do? I'm saying that there exists some algorithm. Then you will search for that algorithm, right? If I show that there is a certain algorithm that possibly can achieve 1 by log of 1 by epsilon, you will search for that algorithm. So that's the other idea. Can we improve or can we find better algorithms under certain theoretical results? Okay, that's the second thing we'll do. Can we discover Okay, and the answer is yes. We are able to discover. Okay, so theory does matter, and theory pushes you to think harder. Okay, so let's quickly do the first part. The first part I won't spend too much time, and then we'll move to the second part. The second part kind of bootstraps around the first part. Okay, so what if we have strong convexity? Can a function be both Lipschitz continuous and strongly convex? Do you think a function can be both Lipschitz continuous and strongly convex? What's an example of Lipschitz continuous strongly convex function? Huh? Yeah, so um, hinge loss plus regularizer. Huh? L2 regularizer. Hinge loss plus L2 regularizer, right? Of course, logistic loss plus L2 regularizer is Lipschitz smooth and strongly convex. Right? Very often we cannot insist on differentiability. So that's also important. We cannot say that it's differentiable everywhere. So we cannot insist on Lipschitz smoothness, but we could add a regularizer and strong convexity, and Lipschitz continuity is typically easy to get. We already seen that. But the thing is, unfortunately, this won't happen. It's not easy. Okay? You need a function to be restricted on a bounded set. Only on a bounded set that's possible. Remember. So this we have discussed earlier. On a bounded set, this is possible. Even Lipschitz continuity and strong convexity. So within a bounded sets, for example, norm W square less than equal to R square. We saw that under that. Otherwise, if you just take a quadratic expression, it may not be Lipschitz continuous. Your hinge loss may be Lipschitz continuous, but not the quadratic term. So just because you slap in a strong convex term doesn't mean Lipschitz continuity is preserved. Okay, so we have to be a little careful. So this example, hinge loss plus a quadratic regularizer, but under a radius bound, upper bound, is Lipschitz continuous and also strongly convex. You have done this. You can look up your table that you had written. So we are not going to spend time writing. So can we get an improved convergence rate in such a case, which is improved over 1 upon epsilon square? Obviously, we now some of you were thinking it will be between strong convexity, so smoothness and strong convexity. We are saying, well, at least it should be better than 1 upon epsilon square. Okay. Let's see how far we can get. Is it 1 upon epsilon square? Let's see. And then we'll, as I said, make a case using some theory. So we're going to so we can improve 1 upon epsilon bound. So it's not as good as you thought. Sorry to disappoint you. You thought it will be landing in between, but this gets us only as far as 1 upon epsilon. Okay. So now you have incentive to work harder. There's something more you need to do. Okay, so now again, this is same kind of boring math. We'll not spend too much time. I don't want to write at all. But it starts with the same old linear algebra trick. You use a stronger lower bound on the above expression. So the stronger lower bound has come from lower bound means strong convexity. Always lower bound means strong. This picture you keep it in your mind. Right? So you got this stronger lower bound. And then we combine it with the original expression. And then we get a norm of GT square. Right? So we know that with Lipschitz continuity, the norm of GT square is less than or equal to gamma square BT square, right? So basically now we do some algebraic manipulation, use Lipschitz continuity here. So Lipschitz continuity, assuming the gradient norm of GT is less than B, and combining with the earlier strong convexity result, we have this expression f of xt minus f of x star is less than or equal to this entire expression. What do we do next? Yes, somebody said telescopic summing. Okay. Also, one small note here. As you said, telescopic summing is a natural question that comes to your mind, right? The only small thing here, difference here rather, is our gamma is no longer independent of the index t. Suddenly, the gamma you see a t sticking out there. So all these are kind of tricks, right? And it didn't happen in a 10-minute span, right? A lot of iterations, trial and error. But it turns out that this analysis benefits from a T specific, step specific gamma, which is actually the case. In reality, you have a T specific gamma. For simplicity, some of the previous analysis, we were able to use a worst case gamma. So we'll do a scheme with a T specific gamma T to make things work. It also, the other thing is we need to make some of these terms disappear. So what would be a choice of gamma T that will help me make some of these terms disappear? Okay. So we have this xt minus x star. I mean, I do telescopic summing, fine. But with telescopic summing, I need consecutive xt's to cancel out, right? So you have to do that home. You can't just land up in a midsem without preparation. So you can't do telescopic summing without any preparation. So telescopic summing is very sacred. Don't just do it. Right? Prepare and do telescopic summing. So all these questions you need to ask yourself. So how do I make this disappear through telescopic summing to a appropriate choice of gamma t? Okay, so far we have this expression, and I want to do a telescopic summing and some gamma t. Now I'm saying, well, how about gamma t being proportional to 1 by t, right? Will it help us? Any guesses? Yes. Minus 1 by t minus 1. So t plus 1 basically. Right. Yeah, but you will have to bring something that has gamma t and gamma t plus 1. See, because this is because you when you sum, you look at 2 gamma t minus 1 multiplied by xt. 1 by t plus correct. So this is an interesting thing here. Gamma, you're saying is 1 by mu t plus 1. There'll be a 2 also somewhere. There's other 2 here. Okay. So some form of t, or basically existence of a t. Okay, I have put a 2 by 2. I don't know why. Maybe it doesn't hurt really. Just simplifies things a bit. Okay. So anyways, mu into 1 by t is gamma in t inverse. Exactly what you said. And multiplying both sides, now you start things getting cancelled out with telescopic summing. So now we are prepared for telescopic summing. So you see that these terms, successive terms will get cancelled out. Okay, so I've done this. For t equals 0 to capital T minus 1, let's just see. I just superimpose my summation here. This expression will be 0 for t equals 0 and t equals 1. And this expression will be 0 for t equals 0. So after summation, on the right hand side, you'll have t times b square by mu. Will be t times. And t into t minus 1 of xt minus x star square into mu by 4. This will remain. Otherwise, all the successive terms will get cancelled out. Okay, so this is interesting. Now, this entire right hand side has a negative. See, these negative terms, should try and see if they can be eliminated. They don't add much value. So minus of t into t minus 1 xt minus x star square, the whole thing we know is this negative is less than equal to 0. So I can just cancel it out and say this is less than equal to tb square by mu. Okay, what have I got? The summation is less than equal to tb square by mu. What will I do next? I just make this a bit formal. Yeah. Now what will I do next between the gray part and the orange part? What's the next step? You guys are experts. You're really nicely suggesting. Remember, I should at least get to 1 by epsilon. Though he's not very happy with me. He wanted it to be somewhere between 1 by epsilon and log of 1 by epsilon. So what could be the next step? Are we done, or should we apply some more inequality on the left hand side? Xt minus x star is, how is it with respect to x capital T? So this left hand side, right? This left hand side is greater than equal to f of x capital T minus x star summed t times. So that will get us a t here. Or a small t itself, summation t equals 0 to, or t equals 1 to capital T, t into t plus 1 by 2. Okay, let's just apply that. Okay, so we have this, I just put it back. Now what I'm doing, I'm applying here. But I'm saying on the left hand side, f of x t is greater than equal to f of x capital T, or strictly greater than. So it is summation of t into f of x capital T minus f of x star, t equals 1 to capital T. But this is the same term being summed t times. I can take it out. So it will become a summation of this small t. Upper index is t minus 1. So it will be t into t minus 1 by 2, f of x t minus f of x star. Right? This is the assumption. F of x star is less than equal to f of x capital T, which is less than equal to f of x t minus 1, or you can say it's strictly less than also. You want descent, not just attempted descent, right? Okay, so that's it. So t into t minus 1 or t plus 1, whatever. I mean, depending on where you sum until. Okay, I have now summed till capital T. So there's t into t plus 1. So you get this expression. And yeah, so for error less than epsilon, we'll need t greater than equal to 1 upon epsilon, order 1 upon epsilon. Okay, so now we are back, right? So for Lipschitz continuous and strongly convex functions, we have the same as for smooth functions. Similar, not same, but similar. But, okay, now I come to the interesting thing. So this is all fine, right? The convexity is there by default, by the way. Even if I say only strong, only smooth, I always mean convexity. None of this holds without convexity. Now I come to this second part of the story. Can we discover better algorithms under certain theoretical results? Here we are saying, okay, it will take at least so many iterations. T is greater than or equal to something, right? Can I establish something? Lower bounds. Okay, sorry. Yeah. So any black box procedure will have an error of at least, right? At least error greater than or equal to something, some term involving T will basically mean that T is less than or equal to some term, right? There's an upper bound on T. The slide is talking about error greater than or equal to, right? In the first case, it's saying if for Lipschitz continuous functions, any black box procedure is saying that, well, it's doing its best, right? Any black box procedure. But I will now present a very adversarial function. That's the proof methodology. Some function, you would probably not even dream about. That's how these are, right? You'll say, kahan se aaya? But the proof will be, oh, it is Lipschitz continuous. It is convex, right? So somebody has worked very hard to do all this, right? So there any black box procedure for certain adversarial function which has been shown, and say at least the error is RB by 1 upon RB by 2 upon 1 plus square root T. So remember, gradient descent gave you RB by square root T. So now carefully study the difference. Okay, RB by square root T, and this set at least RB by 2 into 1 plus square root T. Not far, right? Not far. Lipschitz continuous plus strongly convex. Again, using adversarial functions, right? Adversarial function means someone constructed some, function which happened to be Lipschitz continuous and strongly convex, for which there was at least b square by 2 mu t iterations. Error, sorry. The error was at least b square by 2 mu t. Whereas with gradient descent, we got to be 2b square by mu t minus 1. Again, they look similar, right? Smooth functions. Any black box procedure will have an error of at least 3L by 32 R square T plus 1 square. Gradient descent, what does it do? It says, oh, L R square by 2T. You see a gap? 1 upon T square, and this is 1 upon T. Now do you wonder, well, there's some gap. The actual time it shows us 1 upon 2T. On time, sorry, error. This is the actual error, right? Gradient descent error. So the question is, can some improvement to the gradient descent algorithm help bridge this gap? And that is our answer. Yes, accelerated gradient descent brings them together. Okay. Smooth plus strongly convex functions. Define, so here, okay, kappa is this L by mu, inverse of the kind of conditioning number, right? This L by mu is basically this gap, a ratio. Then any black box procedure, it says, will have square root kappa minus 1, square root kappa plus 1 whole raised to 2t. Whereas gradient descent, you remember some time back we just did this, you had a multiplication and you had 1 minus mu by L raised to t, which can be viewed as kappa minus 1 divided by kappa raised to t. Not too different, right? Because this had square root kappa with the whole raised to t, and this says kappa minus kappa raised to t. Not certainly north and south pole, right? That's fine. I mean, maybe we can get better, but this is the real gap, smooth function. So the gap is not really for strong convexity plus Lipschitz continuity, right? Again, you're disappointed. It is not, we are not trying to push that to the right. We are trying to push strong smoothness to the right. I mean, at least that's what the lead has told us. Okay, so smoothness, but then without strong convexity. So suddenly now we'll be dealing only with convexity and smoothness. So we'll remove the pink and see if we can do better. Of course, we can bring in strong convexity later on, but we don't have results. I mean, we don't know what will happen with strong convexity. So what can we do better? Only for smoothness. Which means if you have an upper bound quadratic, can I do better? Okay, so let me just highlight some important points from here. Okay, so this is the key, case 3 smooth functions. And just to recall, right, gradient descent on Lipschitz continuous functions told us T is at least, T will be at least 1 upon the epsilon square. Here it said T will be at least 1 upon epsilon. Okay. So, and here also we had got T is at least 1 upon epsilon. So we want to see if we can get better. So let's do some introspection. Why would gradient descent be slow? Okay, so a little bit more intuition on the board, but not, again, we'll not do too much theory on the board. So see, the problem is gradient descent, it's suboptimal rates for smooth functions and to a smaller extent for smooth plus strongly convex. I mean, that square root kappa thing also, if you want, think of that also a small gap there. But smoothness, why is gradient descent not exploiting smoothness? That's our question, right? Where see, gradient descent exploits only the local gradient information. And obviously, you can see it's a problem. Now, can we have second order information? Smoothness is about second order. But smoothness is basically giving an upper bound on second order, upper bound on the curvature. So can we respect that upper bound on curvature by adding some information from the progress made so far, so that I know that I don't overstep? See, the issue is I may overstep. If I know upper bound is there, I will not overstep. So can I avoid overstepping through momentum? That's the whole query. Okay, now we'll look. We are going to apply a little bit more intuition here. Just look at the two motivations. First is bridging the gap. Concern is the gap could have been worse for some other function than Nestero would have come up with. So Nestero came up with this idea of momentum, right? The gap could have actually been worse with some other function also. Right? The second motivation is empirically, could the next iterate have been influenced by the series of previous iterates? So it's a very, irrespective of the theoretical motivation, why can't we just exploit the previous iterates? Not a bad idea at all. Okay. And that's what we are trying to show here. If you look at the oscillations here, this function is oscillating so badly, right? This gradient descent is just now, and it's probably taking very large steps. Can we average them out? Can we tell them that, oh, a lot of noise should just get cancelled out? Can we do noise cancellation? That's it. Through previous iterations. That's the second motivation. Can we look at what we call here as average movement? Momentum is trying to add that average movement. Okay, so this is idea. So we look at gradient, the red one. Now there is a velocity. Think of this as, the average movement. And based on that, can I have an momentum update? Okay, so moment actual step is the old step. Old is where the velocity is. Sorry, old plus v hat. So this v hat was basically coming from the gradient in the previous step. Now there are possibilities, multiple possibilities here, right? Let's also look at what this mu and eta are. Okay, so the v is basically about accounting for the momentum. The red is called the momentum update, but v is like accounting for the momentum. And mu is the multiplicative factor associated with the history, which is being captured through the velocity. So there's a tendency to go here. The gradient says here, can I get the actual step? You understand? That's a simple idea. Now, what should this mu be? Right, this mu. Yeah, I go back to the previous step in case it's too much here, right? What should this mu be is the question, right? I should certainly look at the previous, but if I get overweighted by the previous iterate, then I might stagnate, right? So x act is x old plus v hat, where v hat is mu v plus eta k gradient of f. Okay. Now the first point I want to make here is this mu should be a bit regulated. The mu should be between 0 and 1. It should be a bit tempered. Okay. Now, what are the other considerations? As you can see in this figure, the place where I should compute my gradient is also open to discussion. Should I compute my gradient at the current step or after the update? Do a velocity update and then, right? So should I compute my gradient here or should I compute my gradient here? Okay, that's the other consideration. Where to compute my gradient? That's the second step. Okay, let's look at this. Okay, so V plays a role of velocity. It's the direction and speed at which the parameter xi has been moving through the parameter space. Now, if you set set to an exponentially decaying average of the negative gradient, what will be the decay factor? Yes. What's the decay factor here? Mu is a decay factor. Eta is not a decay factor, right? That's what I discussed about this. Mu between 0 and 1 will be a decay factor. This is a decay factor. You're basically saying history is important, but I'm going to have a decay associated with the history. Okay, common values of mu used in practice are 0.5, 0.9, 0.99, and so on. Right? Depends on how much you want to do rapidly, but not less than 0.5. Right? Because if the assumption is there's some smoothness in the function, you don't want history to be like totally discarded. Right? So physical analogy is a negative gradient is basically a force moving a particle through parameter space. So there's a force, but then there's also the inertia associated with the object. So to move that particle, you need the force, but you also have to account for its existing trajectory, right? So when now the point is when the gradient and velocity are in the same direction, you would have the step size largest. Step size will be large, and both of them are aligned. Or when successive gradients are in the same direction. Okay. So step size largest when many successive gradients point in exactly the same direction. They're all very intuitive. Okay, so I'm just trying to now bring out the options associated with where to compute the gradient. Okay, maybe I'll point here. So option 1 is compute the gradient with respect to the old point. That's pretty much what we have shown here. Compute it with respect to the old point. Option 2 is with respect to the new point. After the update, compute the gradient. Right. So which basically means that as per the old update, I won't account for the momentum before computing the gradient. The new one, I look at the accumulated momentum and then look at the gradient. Now the step size consideration will also change in the two options, right? How will the step size consideration change in the first option? I'm computing gradient at the previous update. So my step size, where will my step size be larger? Huh? Yeah, but I'm saying under option 1 or option 2? Option 1, I'll have a slightly larger step size. Option 2, I've already accounted for. I'll be a little careful. Once I've accounted for the momentum, I'll be a little careful. Okay, so this X can be old or new. Okay, now each choice gives you a very different algorithm. So now with this, I have now drawn two different diagrams. Okay, so far I've been collapsing everything into one diagram. We say no, let's have two different diagrams. So what I was showing here was more general, but this is option 1: gradient, velocity, and action step. The second option, what I do is I have velocity. I look at the gradient. I look at the current previous gradient, but the actual step will be with respect to after computing the velocity update. So I do velocity update, compute the gradient, then actual step comes. The previous gradient was used in the previous step. So the gradient was used. The gradient at this point was used, but it was used to a gradient not at this point. To get to this point, a gradient was used at the previous step. You see the difference? I used the gradient at some point after updating velocity, moved here, then applied velocity, moved here, and then applied gradient to move here. Whereas here, in this case, I compute the gradient, I compute the velocity, and then I add them up. Okay. But let's try and write down these actual steps now. This is a notion of accelerated gradient. Each of them is a slightly different variant. So the first one is called option 1. Option 1 is called heavy ball or Polyak. And option 2 is called Nesterov momentum. So Nesterov actually provides very nice, there's a very good book by Nesterov on convex analysis. So there's a lot of, a lot of math that a lot of convergence analysis we derive today is based on Nesterov's book. Okay, so these are the two variants, momentum and the two variants. Now this interesting, the convergence rate goes up from 1 upon t to 1 upon t square. Just with this, right? The exact steps have been written here. So let's look at these exact steps. Maybe I'll reproduce them with some more comments. Okay, so again, remind Polyak, you're computing xt, then you compute the gradient at xt, and then the momentum of xt with respect to xt minus 1. Nesterov, from xt, you look at the momentum direction based on xt minus 1, and then compute the gradient with the momentum update, or the velocity update, velocity update. Okay. So easier to think like that. It's good for you guys to write it down. Okay. Also, a slight subtle thing. The gamma appears with the gradient here, whereas here with the gradient, it's not a gamma; it's an alpha. Basically, you don't treat this to be, the equivalent of a step size, right? Because step size is now cumulative. Here it's actually the step size, right? So it's not gamma here. So I'm just going to write it slightly differently. Okay, so the point 1 in orange. This is the only difference between these two. This is the Nesterov. this difference here. Okay. Okay, so this is the difference. Alpha gradient f of xt, and here you have gamma at the new step. Think of this as gamma f of x new. Right, and this is for. So by the way, I forgot. I was saying this also works for Lipschitz continuity and strong convexity case. It also helps there. Right, that was one of our aspirations. Improve that. It turns out it helps there. While it helps the smoothness, it's motivated by smoothness. Okay, so maybe you can read this apart a bit more detail. Now I've just written down the steps more carefully, but it's pretty much the same as what I wrote. This is the velocity in red, mu t xt minus xt minus 1. This alpha t f of xt is the gradient step. So heavy ball result for smooth and strongly convex functions. This converges in smooth and strongly convex functions. So this gives you L by 2 square root kappa minus 1 by divided by square root kappa. This is looking fine, right? This is looking the same. It's not changed. So heavy ball momentum is not optimal for the smooth case. So if you're smooth, it's not the best. Any thoughts on why? See, we wanted to improve the smooth case, but if it is also strongly convex, it doesn't seem to help much. Sorry, it's not optimal for the smooth case, though it helps in the smooth plus strongly convex case. I'm sorry, the other way. So it turns out Nestero is more effective for the smooth case, or let's see if it is, right? So I'll do this next class, but just to kind of jump guns, right? So this is the accelerated gradient, smooth functions. That gives you 1 upon square root epsilon, which is good, right? It has not got you to log of 1 upon epsilon, but it's certainly better than earlier. Okay. So we'll delve a little bit more. What I would request you to do is, I have a very detailed collab. I'll send a link to that as well. Go through that, because that has a lot of discussion on step sizes, right? How step size can be found. And I also have a very detailed slides on convergence analysis. Specifically, I'll post slides on convergence analysis for Nesterovs, right? Generalized gradient descent. Just have a look at it. We'll just conclude this next time and then move on to stochastic gradient. Actually, subgradient and then stochastic approaches. Yeah. Thanks. So question is, how is the analysis of L and mu getting us better control on the space? It is getting us better control, right? I mean, because of L and mu, we got the 1 upon log of 1 upon epsilon came because of L and mu, right? I don't know what I meant. I don't remember saying deep in space. All I'm saying is, with something like Polyak, a heavy ball, we are able to do pretty much like smooth and strongly convex function which we had done earlier with gradient descent. This did not give us too much advantage. That's all I'm saying. So that's a comment about accelerated, not really a comment about this is always helpful. I mean, this is always helpful for analysis. I mean, in some sense, if you have smooth and strongly convex, all we are saying is things are already so good that you got good enough analysis with gradient descent itself. Thanks.